on the 1st of March as a accredited fellow. I'm going to be around for 3 years at least. I'm working on observational astrophysics and time domain astronomy, and specifically on extragalactic transients. So transients are defined as astrophysical phenomena with durations of fractions of seconds to weeks or years. And they're typically like extreme, highly energetic events that involve the full or partial destruction of an astrophysical object. That's the definition I found online. So I'm going to talk about some transients that happen in the nuclei of galaxies, in the very center of galaxies, where looks like stars are being shredded to pieces, as the cheesy titles hint at, and or spaghettified, as you might have heard it. So why? How is this happening? Who is murdering stars? Let's find out. Yeah, so if you don't want to get spoiled, now is the time to leave. That's the last slide, I promise. Okay, let's go. So we know that in the centers of galaxies, if not all galaxies, but the biggest fraction, lie supermassive black holes with masses of 10 in the 5 to 10 in the 10 solar masses. And the latest confirmation of that is the first ever image of the shadow of a black hole in the heart of the M80 galaxy, taken with the Event Horizon Telescope. And even more recently, we have one from our own Milky Way. But we were able to study, black holes even before the Event Horizon Telescope, and this was done through we were studying them indirectly by observations of active galactic nuclei or quasars, which are supermassive black holes with immense amounts of gas around them. So as the gas gets rotationally, as it impulse forms a rotationally supported disk, an accretion disk, which through like frictional and gravitational force into the emit across the electromagnetic spectrum. But like AGNs constitute like 5%, I found 10% of all supermassive black holes in the universe. If somebody's doing AGN studies, correct me if I'm wrong. The key point is that they're a very small fraction of all the supermassive black holes. So what happens with these black holes that they do not have vast amounts of gas around them, or it's so small that they're not luminous enough? Is there a way? So we call those supermassive black holes dormant or quiescent. So what about those? They constitute a vast majority, and they're very interesting astrophysical objects. So is there any way that we can probe their properties and study them? So this is where tidal disruption events enter the picture, or abbreviated as TDEs, where imagine a star in the like orbiting around a supermassive black hole. So the gravitational potential becomes so strong that the star gets elongated until it gets shredded pieces. Yes, so they say picture is worth 1,000 words. Maybe a video simulation is worth 1,000 pictures. So I put a video here, and before it starts, it's supposed to be the star, and this is the black hole. So imagine the star falling in a parabolic orbit. So as it approaches the black hole, the gravitational potential, like the tidal forces, elongate the star. And when it reaches the so-called tidal radius, it gets ripped apart. Half of the debris escape in unbound orbits, while the rest gets bound into highly eccentric orbits, and the debris form a thin stream that self-intersects, shocks, and then the debris are supposed to form an accretion disk around the black hole. So both stream collisions and accretion are supposed to produce electromagnetic radiation. And all in all, this is the process that gives rise to the flux of luminosity that our telescopes observe. And here's a schematic of what we just saw. So the star is coming in a parabolic orbit, it gets elongated, and when it reaches the tidal radius, which is like a function of the black hole mass and the stellar properties, the stellar radius and the stellar mass, this is where it gets disrupted in the tidal radius. So an interesting thing that was predicted from theory here is that if the pericenter distance of the orbit is larger than the tidal radius, so if this beta parameter, that is less than 1, then we're supposed to not have a full disruption, and the core of the star, so we have some disruption, some of the material gets stripped away and gets whatever it does there, and the core escapes only to get back again and again and again. This is what we call a repeated TDE or a partial disruption. Yes, so what I wanted to, so yeah, all this sounds very spectacular. Supermassive black holes feasting on the debris of stars, and we saw in the video, it must be like really stunning to watch. And here's how it looks in reality. So this is what we observe, some pixels, some illuminated pixels. Remember this happened in other galaxies, right? So now jokes aside, this is how we discover transients in general and TDEs. So I'm gonna talk very quickly about that. So this is a galaxy, just sitting there doing nothing or doing whatever galaxies do. And then we have all these wide field optical surveys that scan the night sky and take nightly images of all the tiles they're supposed to observe. So these are the science images, as we call them. But the wide field surveys have got deep templates of all the night sky before they start operation, like this, let's call here reference image. So every night, whatever they observe, they immediately remove the reference from the science image to get what we call a difference image. And usually, this is just noise, as you see around here. But unless a transient has happened, suddenly you can clearly see that something's going on. And in this case, you can see how the nucleus of this galaxy got really illuminated, and most of the times transient outshine their whole galaxy. They're that illuminated. And so a good question is how do we know that this is what I talked about? Why it's not a supernova or something like that? So there are many answers to this question, but I think the most important one is that if you look here, this is the Schwarzschild radius, which is a function of the black hole mass. So the larger the black hole mass, the larger Schwarzschild radius, which defines the size of the event horizon. So theory predicted that if you do the math, that for black hole masses above 10 in the 8, then the event horizon is larger than the tidal radius. So by definition, nothing escapes from the event horizon. So we shouldn't be able to see TDEs that happen around black holes larger than this mass. And as we keep populating the samples, you can see here this is the rate of TDEs, and as a function of the black hole mass, with whatever ways we believe we can measure the black hole mass. So you see that the rates do plummet after this 10 in 8, which is kind of a nice confirmation that these events are what I described in time. Okay, and so now a bit of a history, TDE history, of course. So TDEs were predicted by theory since the late 80s, and within the classical picture, the idea is that through various processes involving what I talked about, the debris becoming a thin elongated string that self-intersects, and this makes kinetic energy get dissipated, so material starts falling in the black hole. So through this, then the material settles to a standard thick accretion disk around the black hole that should have temperatures of, I don't know, like 1,000,000 Kelvin, which means that they should be brightly X-rayed. And indeed, we started discovering TDEs in the X-rays in the late 90s, and then with the Galactic satellite in the UV. And then came the rise of the wide field optical surveys around 2010. So we saw things that we were definitely not expecting according to the basic theory. So we started discovering many TDEs that were bright in the optical UV TDEs, we call them, with temperatures of like 10,000, around 10,000 Kelvin. And so there are still TDs that are only X-ray bright. There are some that are optical and X-ray bright, but like most of them, the big numbers are only in the optical. So this definitely challenged our understanding of what's going on. And this gave rise to different emission mechanism scenarios that are debated to date. And it's important to pin down the emission mechanism because this can, in hand, let us know of the properties of the supermassive black hole, which is kind of the whole grain of TDs, right? To learn things about the supermassive black hole. So I'm going to go through these scenarios a bit. So this is the so-called reprocessing scenario, where the idea is that due to super angular accretion, there are optically thick outflows early on that they form this kind of reprocessing photosphere. We call it the Eddington envelope around the accretion disk. So all the X-rays from the accretion disk are reprocessed within this processing envelope to like optical and UV wave. And so with time, this was updated to a viewing angle dependent scenario, where the idea is that if we're looking face on, then we see an only X-ray TD because the X-rays escape through this funnel and maybe sometimes relativistic jets. If we're looking edge on, then everything is reprocessed to optical UV, so no X-rays. And there are some intermediate angles that can potentially reveal X-rays and optical emission. So this is the viewing angle dependent scenario. Then we have the extreme collision scenario, where the idea is that during these extreme collisions that I talked about, there should be strong shocks that this is where the optical and UV is produced, and not by any reprocessing. Later on, so these two are the main competing scenarios to date. And then we have kind of variations of those. Most recently was this collision-induced outflow scenario. I'm not going to go into details now. In my head, it's a bit of a combination of the two aforementioned scenarios that I talked about. And even more recently, this cooling envelope model that tried to, by Brian Metzger, try to explain some observables, like the constant color evolution that we see in this, which is a bit weird, constant temperatures, and some late time flattening in the light curves, like we see in some of them. So this is still under debate. We don't know what's happening really. And thanks to the wide field optical surveys, we're now observing around 20 TDs per year, and we have identified around 150 like strong candidates. And of course, all these numbers are supposed to change by orders of magnitude when proving like previous size operations. Okay, so now about some basic properties of TDs. So as I said, they're supposed to have they have temperatures of 10,000 to 50,000 Kelvin, and they have constant colors. You can see like the evolution, they're not cooling. They are well characterized by blue continua that are supposed to peak in the UV. And these continua are dominated by broad lines around 10,000 kilometers per second, 20,000 kilometers per second, always in emission. There are no absorption lines or cyclic profile, I mean, like in supernova. And now about the spectral properties, which I'm going to focus on. So in an early work by Yair Agavi, it was shown that these lines are of hydrogen, so Balmer lines, it's alpha, it's beta, and helium, specifically this helium-2 line, 4686 angstrom, which is like very typical in TDs. Broad lines, as we said, and it was also shown that it looks like there's a continuum of hydrogen to helium-rich events, with some events showing like both elements, hydrogen and helium. And as years passed, we kept like populating the sample, and indeed keep seeing this continuum of hydrogen to helium-rich events. Something that we started noticing was that looked like that in the early spectra of some of the TDs, we were seeing kind of these profiles that were blue shifted to the rest wavelength, and they have extended red wings. And this was explained in some theoretical papers with within the reprocessing scenario, that these were attributed to early, like optically thick outflows forming an electron-scattering dominated photosphere. So they were supposed to give these kind of profiles, and you can see for two events that indeed the profiles, the actual observations nicely match the theoretical profile. Yeah, but things weren't that simple after all. It wasn't just hydrogen and helium. I'm going to go now through a series of discoveries in the spectra of TDEs, and it all started by some TDEs that seemed like they had some nitrogen-3 lines in the spectrum, and then it was established in this paper by yes. Right. That there are TDEs that show this nitrogen-3 and sometimes oxygen-3 lines, termed Bowen lines, because they're coming from a mechanism called Bowen fluorescence. And so the strongest of these lines is this nitrogen-3 at 4640, which unfortunately is next to helium-2. And the other one is at 4100, like literally on top of H delta. So things are blended. And one thing to notice here is that the Bowen line seems to be in this class of hydrogen and helium TDEs. And this is not random. You need helium in order to trigger the mechanism. And we also need a source of like extreme UV photons that they need to ionize helium-2 to helium-3. So then it recombines and emits the photons that are needed to trigger this cascade of the Bowen fluorescence mechanism. So here's how a closer look to this heavily blended, like 4,000 to 5,000 angstrom region looks like. And here we were kind of fortunate enough that the lines were narrow for a TDE, so we could see that the two different peaks in helium-2 and nitrogen-3. This is not always the case, especially for low resolution spectrographs. But one a good way to identify a nitrogen TDE is that if this were H delta is, so if this is H delta, it doesn't make sense that it's that stronger than H gamma, right? Or H gamma should be stronger than that. So, and yeah, and I can show you this if you're not convinced. So these are the likelihoods of a repeating TDE, or at least what we believe is a repeating TDE. You can see the two clear peaks with around 2 years distance between one another. And if we look at the spectra of both these flares, you can see this like booming nitrogen-3 profile here in both flares. Yeah, and since I'm talking about repeated TDEs, just to say that this is still, it's not like 100% established, because we have only seen very few like second flare in the nucleus of a galaxy that we already have a TDE. It's one of the cases. So it's still debated whether there can be two completely unrelated TDEs or events in general, or if it's the same star getting disrupted again. So if they show similar spectra, is a good confirmation that it could be a repeat. So spectroscopy will be a strong tool for that. Yeah, so there is more. And we discovered this class of iron-rich TDEs, where we see this forest of singly ionized iron lines, again in this heavily blended region. And this seem to show the oxygen-3 Bowen lines as well. Keep that for later. And this is reminiscent of narrow line Seifert 1 by Aegean Galactic, that they show these lines. And you need a compact accretion disk and high density optically thick material to give rise to these lines. And this is in line with the fact that these events, they're rare. We haven't seen many of those, but they seem to have strong X-rays as well. And again, in line with that, they could be viewed face on indeed, like the narrow line Seifert 1 galaxy, but by definition, they're viewed face on. For here, in this TDE from 2018, we saw these clear double-peaked profiles in the Palmer lines of this TDE, which was attributed to viewing an accretion disk from intermediate to large angles in order to see the peaks. And this event also showed mild X-rays. And it's not the only one that shows a double peak like profile in the Balmer lines. And here's an example where we identified a triple peak TD, and this was attributed to viewing an elliptical accretion disk almost edge on. And even more recently, this TD, this is the most close by TD that happened in the interacting liner galaxy 196.799. And so I wrote a paper about this one. We saw this like broad outflow dominated profiles, GCH alpha, like I talked about before. So what was really interesting here is that we saw this, maybe I should have this plot a bit larger, but we see this weird feature, which is like 10,000 kilometers per second blueward of the rest wavelength of H alpha. So this was helped to understand because the first time we see it, and yeah, so one good question was why we haven't seen it in any other TD, and then we were thinking, is it like a fast-moving component of H alpha, like we see in supernova? Is it that we just saw this early collisionally induced outflow completely direct to us and happened to have this alignment, so this was moving towards us? I'm not going to go into more details here, but this is another thing to prove that still individual events bring something new. We're still in this era. And another interesting aspect, so here is this TD from 2019, and you see it had some like typical light curves, peaked and then declined. So first, we noticed that this one shows this huge mid-infrared echo, which is still ongoing. And because of that, this was the first TD with a JWST spectrum. And so apart from this mid-infrared echo, we saw like 3-4 years after the optical peak, there was X-ray emission. And spectra showed that there were these very narrow, high ionized iron lines, which are called coronal lines. They're not only of iron, there can be other species, but you can see the iron line here. So this was interesting because so this is just pretty much the host galaxy spectrum, TD3. It just has the coronal lines on top, right? And why this was a nice observation, because it was predicted by theory that these extreme coronal line emitters, which are just galaxy spectra with coronal lines, it was predicted that it could be powered by TDs because you need an X-ray ionizing source to trigger these lines. And here, with this observation, we pretty much saw the first kind of clear proof that probably it's a TD that triggered this coronal. And yes, so I said we saw a delayed X-ray emission, but that was not the end of the story. We discovered quasi-periodic eruptions, QPs in this TD, which you can even see by eye, these super nice observations. So what are QPs? As the name suggests, they are short-lived, like they last some like few hours, bursts of X-rays, and they're repeated. So here they're repeated after every 42 hours on average. And so QPs are like a very hot thing these days, literally and metaphorically, because like after 2020, there are like several nature makers on QPs. And this observation was very nice and very important because it was again speculated that it could be TDs that power these QPs. So here is the scenario. The idea is that if you have an EMRI and three-mass racing spiral, this involves a supermass black hole and a compact object, which can be like a stellar mass black hole, a neutron star, it's really important. So as these things orbit around each other, if you have an accretion disk around a black hole, then every time the other compact object crosses the accretion disk, you get a burst of X-rays. But the question here was that, these are not AGN, so you're not supposed to have any like that big accretion disk. And this is where TDs enter the picture. the idea was that if in this system a TD happens as well, so if a star falls and gets disrupted, then with years an accretion disk is formed, and then whenever the compact object grows into this, you see the QP. And this was like the first like observational proof that this would indeed be the case, or at least in this one probably did. So yeah, super cool observations. Okay, so yeah, it looks like things were not as simple as we thought in the beginning with the hydrogen and helium picture. So we're still trying to understand what causes all this diversity in the spectra. And modeling is one approach. So what about modeling papers? Well, there haven't been many up to now. So there were these two, one by Nathaniel Roth et al. 2016 and by Edward Parkinson et al. In 2022. So they managed to successfully reproduce the Balmer and helium-2 lines and also reproduce some other qualitative features. However, they failed in other aspects as they couldn't reproduce the Bowen lines, and sometimes they were giving like disproportionately strong helium-2 or like oddly safe helium-2. That's not what we see. And then I talked about the early time profiles. At least there we had a victory that we managed to explain this blue shifted profiles with extended red wings with an electron scattering dominated photosphere. So this was my slide up to some days ago, where a new modeling study appeared, which I'm an author of as well. I'm very happy for this work. So this made me change my slides. So this is a spectral modeling work, again within the reprocessing scenario, running radiative transfer simulations of like optically thick outflowing envelopes of solar composition. And so this work manages to reproduce continuum properties and spectral features, also hydrogen, helium-2, and Bowen lines, finally, in emission. And so according to this work, what is really important for this continuum to get this continuum of events is the ionization state of the reprocessing envelope. So this is defined here by this modified Xin parameter, which is a function of the injected luminosity, so the luminosity from the central engine, which in our case like an accretion disk, to the envelope mass. Okay, so I'm going to refer to the results of this study as we move on. Okay, yeah, so what about sample studies? So I like to show this to people. This was from an TD-only conference, a week-long TD-only conference, 2024. So if we make a search in the 94 titles of talks and abstract of this conference, so the term spectrum were appearing 3 out of the 94. So you can see that like TD spectroscopy is a relatively unexplored field. So about sample studies, the only one that I know of is my first paper ever in 2022, where we studied 16 TDs with a cut to events 2019. And this cut is because we also need to get a host galaxy spectrum after the TD is gone in order to subtract the host galaxy from the TD, which are hellish process, but I'm not going to go into details now. This is more technicalities, but just to explain why we had to put a cut back then. And I'm going to focus here on the results mostly of H alpha because it's the most prominent line in TDs and it's the less blended, as we saw, and safer to draw conclusions from. And I'm going to compare the results of this study with this new modeling paper that appeared some days ago. Okay, so here is the evolution of the velocity width of H alpha, the Kubica maximum with time, but I'm color coding. I don't like most of the plots from my first paper, so I would do them much differently now, but now I have to stick with them. So I'm color coding for Bows, for TDs that also showed the Bowen lines in their spectra and those that didn't with orange. So what clearly we see is that the nitrogen-3 rich TDs have lower velocity width in the H alpha line than the rest. So this is interesting. And why is it interesting? Because in a photometric population study, we established that the nitrogen 3 TDEs, the green squares here, show smaller black body radii than the rest. So uh, if the black body photosphere size correlates with the line emitting region, if we take this into this true, which must somewhat make sense, then if the line widths were set by the kinematics, you would expect that the bound TDs with smaller radii should have larger velocity widths. But we do not see that in this plot. We actually see the exact opposite. So we say that the line widths are not driven by the kinematics in TDs, and we suggest that they could be driven by electron scattering, which is in line with this early modeling works that suggested like that TDs have stratified photospheres and electron scattering dominated photospheres. And this was also proved by other observables. For example, the first spectropolarimetric study of TDs also finds reasons to believe that electron scattering is dominating around the central length. Okay, so yes, I said that I will be bringing up the new modeling paper. So here, it's a plot, again, of the H alpha fluid have maximum, the velocity width, and you can see there's a color bar. Here are larger velocities, smaller velocities, the blue. So let me make a reminder. In this paper, we say that everything depends on this modified ionization parameter, which is a function of the injected luminosity in the y-axis, the envelope mass. So this means that the ionization is stronger in that direction as we go there, which then the temperature is in line with the ionization, here in high temperature in order to be ionized. So higher temperature, smaller radii. So if we now check, we said that these TDs have smaller radii, so they should be somewhere here, and this means that they should have the lower widths, the lower velocities, and this is exactly what we saw in the observational results. So this is a nice confirmation. We're happy to see this plot. And now, so this is the luminosity of H alpha now as a function of time, and this the y the 0 point in the x-axis is where the peak of the light years, where it occurred. Else, because we were dealing with older events, some of them were discovered after peak. So for these events, it is the date of the discovery. So if we look closely, you can see that the H alpha luminosity looks like it lags the optical light year. And here is a visualization of these lags. So the circles are the optical light years used to determine the peak, and the markers with the dashed lines are the luminosity of H alpha. So on the left are events discovered pre-peak, on the right events discovered after peak. So we can only put lower limits for the lag for this trigger. So these lags here like span range of 7 to 40 days. And here's another visualization of these lags, again with the same color coding as before. And that's these are the lower limit events, these three. So two things, and I plot the time lag, sorry, I didn't say that, against the peak of the black body radiation. So like two things to take away from this graph is one, that it looks like there is a correlation with smaller black body radius and the smaller the lag, and also it looks like the bound TDs have smaller lags than them. So about these lags, they're reminiscent of what we see in AGN, brought by reverberation mapping studies, where we have light echoes of the emission lines from the broad light region. And according to this scenario, then these lags would then be translated to the order of 2 to 10 to the 16 to 10 to the 17 centimeters, meaning that this is where this material giving the light echo should be. So the line emitting region. But this then would mean that the lines, or H alpha in that case, is emitted 10 to 100 times further out than where the photosphere lies, which sounds a bit large. So with tried to explain that in the paper, and one thing we suggest is that there could be reprocessing material closer than that, but if it has electron densities of 10 in the sixth, 5 times 10 in the sixth, then this would lead to recombination times of this range matching the lags. Because in AGN, the electron densities are like 10 to the 10 to 10 to the 12. So the recombination time is supposed to be instantaneous. So we suggest here that there could be a reprocessing material closer, but because of these electron densities, give this kind of lag to the lag. But yes, this is not as clear as in AGN because we do not have such a good cadence in the lines. There are many things that make this a harder study in TDE designing. So I'm moving on. This is again the H-alpha luminosity in the y-axis, but I plot against the black body temperature and radius taken from like photometric studies in the literature, where these properties were interpolated in order to match the spectral epochs. That's how I can plot them together. And if we focus on the radius one first, so we see that there is a like monotonic and maybe even linear relation. So the smaller the radius, the smaller the H-alpha, and vice versa. So this was not surprising. This was predicted by these early theoretical works, saying that for smaller envelope, for smaller reprocessing envelopes, the H-alpha is supposed to fade hydrogen emission in general. This is what they were suggesting, and this is pretty much what we see. And then another nice diagnostic is the ratio of the luminosity of the helium-2 line over the H-alpha line. So there's a luminosity ratio plotted against the black body radius, and we see that looks like for smaller radii, the ratios become larger. So again, the same idea here. In this theoretical paper, they say that smaller photospheres would suppress the emission of hydrogen because it's self-absorbed at most radii, while helium-2 is thermalized in a greater depth, hence emitted over a greater volume. And now we have this new study. So here things are very easy to interpret. You can see the color bar shows the ratio. Here we have a increasing radius. So we find that for smaller radii, this ratio should increase. This is what we see here. And this indeed points to a stratified photosphere where H-alpha is emitted, but more outside than the helium-2. And it shows that the gas conditions are important for what we see, because there is also a debate whether what we see depends on the composition of the star, but it looks like that this really depends on the gas, on the specific gas conditions. Right? So it's not only what the star had. And now the temperature plot, so we see this kind of inverse power law relation. And in the paper, we see that for temperatures, black body temperatures above 30,000 Kelvin, H-alpha seems to fade fully. So we say this could be an ionization effect. If the line emitting region again is correlated with the photosphere, this means that things get ionized. And again, bringing up a plot from this new paper of Thompson et al. I forgot to name the author. So this is the hydrogen ion fraction as a function of the ionization state on the temperature. So you can see that for this range of temperatures, for small temperatures, we have hydrogen-dominated TDEs because neutral hydrogen starts rising. So indeed, they also find that this ionization effect. This when for small temperatures when neutral hydrogen starts popping up. And another nice diagnostic, let's say, is the helium-2 to the helium-1 5876 luminosity ratio. And here, again, we see kind of a dependence against the black body temperature. For smaller temperatures, the ratio seems to drop. And even like for these events with the lower temperatures, we didn't see helium-2 at all. So again, we said that this would be an ionization. We're probing the ionization of this envelope or whatever it is. And as you might have guessed, I'm bringing up a paper from plot from this paper again. So this is the helium ion fraction this time. And you can see that as the temperature decreases, then the ratio of helium to the red here with helium-1 like just plummets to this region. And in this, what we also see. So yeah, very happy to see the results of the paper today. And so here, these are things we've seen already. It's the same plots, but they're color coded now. So I'm color coding. Let's think of these events, the hydrogen and helium events. I plot with blue the events that are nitrogen-3 rich, and with cyan these events that show these iron lines and the oxygen-3. While the plain hydrogen events, I plot with red the ones that show double peaks or double peak-like profiles, while with orange these ones that I call plain. And what we wanted to do here is try to explain all these like subclasses or spectroscopic subclasses and the like unique and diverse features that we see in some TDEs within the reprocessing viewing angle dependent scenario. And we need to see what the X-rays did in order to do that. So this nitrogen-3 TDEs, only 1 out of 6 in our sample saw the X-rays, so we don't usually show X-rays, while the other ones show strong X-rays, the iron-rich ones. Well, and this as a class, we said they show small black body photospheres. I'm trying to put a puzzle together here. It's very qualitative. But so the hydrogen ones have large black body photospheres, and the double peak ones show mild X-ray emission, while the other ones we didn't detect any X-rays. So I want to see how this would fit the viewing angle dependence, right? So we suggest in the paper that we could be viewing these like iron-rich ones face on. So we see the strong X-rays as well, while the Bowman ones we see the edge on. So there is no X-rays, everything's reprocessed, and this ties well that the Bowman mechanism needs a lot of scattering to happen. So it makes sense that we have a dense photosphere. And then the hydrogen ones could be viewed from intermediate angles. And because like larger photospheres, less dense, so maybe the like unique features like double peaks, mild X-rays happen to escape or not escape. So we can see them based on some unique disruption property, right? Like the optical depth of this photosphere, etc., etc. So as I said, this like qualitative scenario, and we definitely need to check, to make the same study with events after then, with the newest events, to see if it stands the test of time. And this is a project I have in mind of doing to write paper number 2. So as I said, we need good sampling, no more events without prefix spectra, so we can also study the formation of the lines, and no more events with 2 or 3 spectra like I had in my paper. So I've been trying to achieve that with a program that is running several years now at the Nordic Optical Telescope, which is a TDE dedicated program. So you can see here the light curves with circles, and the dashes on top are where we have spectra. So I can proudly say that like 5 of these 9 events were classified by me, and 4 of them were classified pre-peak, which is really hard to do because, first of all, they're rare, and then they're heavily contaminated by the most frequent supernova class, 1A supernova. And after peak, it's easy to distinguish, but before peak, they look very similar. They have similar colors, so it's really hard to pick targets. But yeah, anyway, you got the point. So yeah, this can lead to a study, the lag studies, the spectral property study, and even like the first pre-peak spectroscopic sample study. So if we focus, and I'm getting to the end of the talk, so I want to focus a bit on this top event, this 2024 WSD. And as I told you, we're still in TDEs in the regime that single papers might bring something new to the whole picture. So this was a very interesting one. So some of its properties was that it was very blue and very hot. It was one of the hottest I've seen. At peak, it was around 40,000 Kelvin. And So it showed these early broad outflow dominated lines. Now you're experts on this as well. You can see these profiles. And it seemed to also show nitrogen 3. Again, you're experts because why? We see the 4100 line here. But nothing new, like nothing very deep. Only the temperature was interesting. Until we got this spectrum with the NTT through the best collaboration, which seems like the nitrogen 3 lines suddenly narrowed down 5,000 kilometers per second, while the helium 2 and the H beta, the H alpha still showed a broad like line. So this was interesting because does it point to what we see in AGN, that there's like a broad line and a narrow line region, and we see this transition. So we thought that this merits an Exuter DDT, and this actually went in the DDT, and with some delay, it was accepted. We got the spectra, and so we have a nice spectral series for this one. We even got the now back behind from the sun, so we have a host galaxy spectra, and this paper I'm also trying to write right now. So like very quickly, which we mean here, this is the entity spectrum, and this is the first Exuter spectrum. So what we saw is that it looks like the Balmer lines followed, and you can see here H beta clearly also narrowed down, H gamma as well. So this was 1 week difference from the spectrum. So I'm looking forward to write this paper and to maybe even try to model and see why we see this transition from broad to narrow and why the nitrogen 3 lines did it first. And this is my last slide. Since I'm talking about optical and UV TDs, I thought of saying something about the UV spectra. So now we have a handful of HST TD spectra. And so what is interesting to see there? So one thing is this semi-forbidden nitrogen 3 to semi-forbidden carbon 3 ratio that in this early study of Young et al. In 2017, for these 3 TDs, they found a lower limit of 10 in this ratio. And yeah, why is that important? Because this ratio is particularly robust for estimating the corresponding abundances of these ions in the emitting gas, because these two have similar critical densities and excitation energies, so they do not depend on the specific gas conditions, like the optical nitrogen 3 lines. And this means that if we have then the abundances of these elements, we can calculate the stellar mass, or we can pin down the stellar mass of the star that got disrupted. Right? So in this paper of Mockler et al. In 2022, they visualized that nicely. So for the upper limit of 10 in these 3 TDs, we can put a lower limit of 1.3 for the disrupted star. And and why is that nice? Because with UV spectroscopy of TDs, we can study and probe the stellar populations in the nuclei of other galaxies. So this is it for me. Thank you for your attention, and I'll take any questions if you have any.
Thank you, Panos. I have a question. Do you think one single model or interpretation can explain the whole populations of TDE because of the diversity?
How do you mean it? Because you mean that there might be...
Well, if it's just one process that you can explain everything you see, or maybe there are 2 different things.
I think, yeah, to be honest, I like this. I don't know how I can find it. This collisionally induced outflow scenario I talked about at some point. I think it makes more sense. And I tried to push it a lot in this first paper. Well, maybe it's easier to do it from the computer. Just a second. We're getting a lot of spectra episodes there. Okay. So that's why I said that this one in my head is a bit of a combination of the first two, because there's that the black hole is not in the center of the reprocessing envelope in this scenario, because and this collisionally induced outflow stems from where the debris collide, right? Which let's say, and then this is the center of the outflow. But still, the black hole then is within this. You get the point that the debris stream collide, and then this outflow happens, which makes a reprocessing envelope. So the black hole is still within this thing, but is also, so the center is where the things collide. So if you think this can give many different observables, depending on where you see that from, right? It could be from the side of the block. So then material also starts accreting, but depending if you're here, you see something. So this is much more complicated to pin down than just this, right? Because here the black hole is in the center, so it's kind of straightforward what you might expect. But here, things will be more complicated, especially if you think that the SOX itself also produce luminosity, and then the reprocessing produced optical UV and luminosity. And yeah, even like conceptually, if you think of this thing, it sounds like a complicated process. So I'm not sure if we can just so easily just by one simple toy model kind of but we have to try that.
Yeah, thanks a lot. Can you go to the quasi-periodic eruption?
Yes.
It's a basic question, maybe I missed something.
Yeah.
Because it's quasi-periodic, and there is a quite difference between the recurrent types.
Yes.
So the idea for those differences is that you have this material that, because the orbit, of course, is very stable, the compact object, but then what causes the difference in the recurrent time that the debris are moving the distance?
It's a great question. I think it's explained by, let's see, because here you see kind of a tidal light. Imagine if if this is not perpendicular,
yeah,
right? But if the orbit is more inclined, then you would have different times. Let me think of this. Let me think this a second. Yeah, so if this oval was more kind of, imagine it being like that this side of the oval is that this is closer to the accretion disk.
yeah,
right? So let's shift all these things here. So then you have when it passes from here and here, this happens. This has much smaller time difference than when it goes from here to here.
yeah. Okay, but then
So
you
you
see,
see kind of some differences in the.
yeah, but there you see that let's say 40, 50, 40, 50, but then 50, 40. So,
Yes.
so that's a. I mean, unless you have that these debris are moving, so that
I think again this. I think, but I can check that. I can send some papers, but I think these are. It's attributed the differences. I think how this the geometrical effect and how this can be. Yeah, I think so, but I can like take a look into the papers and we can chat about it more. But I have a memory that this is no. I mean, it's very interesting. Right? So I think this is kind of the idea why you see something changing the orbit in the like cases.
Yeah, so I also have a question about this. So you're saying, or these people are saying, that this comes from a TDE that took place sometime in the past. We don't know exactly when because we didn't observe it. No,
No, we observed it.
we observed it.
Yeah,
Okay.
2019, and it was a very constable. So you had the it looks very squeezed, but we had a
Right.
take the light curve, it rose, declined, gone, and then we saw this corona line.
And then the QPs only started after that.
Yeah.
Right.
Or at least, I mean, because I know the author, this observation happened by like near Lagrange, then they had a HST plus Chandra program to study post galaxies of TDEs after they happen.
Right,
Something completely
right, so
different.
they don't know.
So they just got these observations that is when it happened that the Chandra observed, right? And even by eye, they saw that, something crazy had happened here. The
And
beginning
you
is of this like wrong.
So this is one case. Do you have QPEs in other objects? Are there, so to say, orphan QPEs without TDEs connected to them?
I'm not sure about that, but I think so. I definitely remember a paper with Phil Evans that there was no optical emission, but as you say, it could be that was missed, right? And this paper here was like in 2022, so this could be back then when we were not kind of getting all the optical thing.
And what is how long are we expecting to see QPEs? What is the lifetime of the disk? Do we
Good
know?
question.
Is there a theory?
These days, people try to, and I talked very briefly at some point about sometimes we see late time flattening in some PDs. So imagine here, but then you kind of saw optical emission here. Actually, this one does so. So this one, indeed, it didn't completely fade. If you go deep enough, take deep photometry, you can see that it has not completely vanished. So
The disk persists.
yes, and now there are papers to try and fit the photometry and stuff with these models to see how long they could be growing. But I'm not sure about it, but I think the idea is that they could stay for long. But of course, that doesn't mean how long. I think, again, that we're talking of like, I would say 100 years, but I'm not sure about that. I might, so don't take this with a pinch of salt, but I think the idea is that they will stay for
Right.
100 years. But yeah, this would be interesting to talk a bit with people that study, X-ray binder, that study X-ray, then they know more things about actual accretion disks and how they should behave, or than if we, because we kind of have estimates of what's the stellar mass that should go to this disk, right, from a TD. So it's nice for people to say, like with this mass, yeah, you can make it.
Okay. Please, we just don't wait for the.
Just close the connection now. My computer and please.